So what we did last time, we did the Jacobi method. This is what and we said that the Gauss-Seidel, which we'll be doing today, as here in this question it says, using Gauss-Seidel, it is nothing but a modified version of the Jacobi method. So when we have something like this, I need to write the equations, these three equations, in terms of x1, one equation, then x2, a second equation, and then x3, a third equation. This is the first thing. So I have to keep x1 in one side, the rest in the other side. So from this, you can say that x1 will equal to 1, which is this, minus 3x2, so I move this to the other side, plus 5x3 divided by 12. Here, now x2 will equal to 28 minus x1 minus 3x3 divided by 5. And finally, x3 will equal to 76 minus 3x1 minus 7x2 divided by 13. So with this is the first thing. Okay. Now, what I want to find is the following. I want to find x1, x2, and x3. And the vector or the first assumptions are given to us. So I know that x1 is equal to 1, x2 is equal to 0, and x3 is equal to 1. So this is the first assumption. Okay. So now when we move from here, I need to find from this. I want to find x1 first iteration. Okay. So this vector is 1, 0, 1. This is the starting. This is the start guess. This is the start of the iteration problem. So x1 is equal to 1 minus 3 times x2. What is x2? This is x1. This is x2. So this is times 0 plus 5x3. x3 is 1 divided by 12, and this is equal to 0.5. So now, regardless if I use Jacobi method or Gauss-Seidel method, it doesn't really matter. All of them will be having the same results. The first one. This is 5. Sorry, I forgot. Thank you very much. 5. This is 5x3. Okay, so it is 6 divided by 12. It is 0.5. Okay. Now let's go to x2. And here now, when you start x2, you will have different values if you use the GS method or the Jacobi method. So let's start with the Jacobi. If I want to find x2 first iteration using the Jacobi method. If I use the Jacobi method, then it will be 28 minus, this is for the Jacobi method, x1, I will go back to the initial guess, which is 1 minus 3x3. I have only one value for x3 so far, which is the initial guess, which is 1 divided by 5. And if you do the calculation, you will find that this is equal to 4.8. Okay, so this is the Jacobi method. And if we go to x3, I will do the same thing. I will use x1 and x2 from the initial guess. However, Gauss said, or Gauss-Seidel, these are two scientists, they said, no, why I have to use the initial guess? Now I have two values for x1. This is a value of x1, which is the initial guess, and they have another value which is 0.5. So Gauss-Seidel says I will use the most updated value. So instead I will use here 0.5, and the value here would become equal to 4.9. Okay. Finally, my x3 equal to 76 minus 3 x1. Now we will use the most. Let's stick to Gauss-Seidel. We know now what is Jacobi. We'll use the most updated value, which is 0.5. Okay, minus 7 times x2. Again, x2 has two values, 0 and 4.9. I will use the most updated value divided by 13. And this will give me the value of 3.0923. If I use 5 significant digits, these are the values I will have. Okay. So now the question we will use using 2 iterations. In the quiz, when I ask you to solve, I will not ask you more than 2 iterations. But in the simulation, I will ask you until you reach certain error. Let's say error 1%, 0.5%. So I will specify to you the error that you have to use it as a criteria before you stop your iterations. So this is the one that I just did. Now we will always use here the absolute relative approximate error. So always I will compare my current value with the previous value. So my current value that now I found is 0.5, 4.9, and 3.0923. So this is my current value. My previous value is 101. Always, most of the time, not always, most of the time, the first iteration will be far away from the initial guess. Okay, so you can see here there's a huge error between these two values. This is expected. Okay, so if you do the error, you see it is 100%, 100%, and 67%. Now what we do? Now, this is my x1, x2, and x3. We go and repeat the same thing. We go now to the second iteration. Okay, and we keep doing this. So if we do the calculations, you will find that x1, x2, and x3 is equal to this. Okay, and if you want to see the full picture, this is now these are the new value. This is the old value. So let's see the error. Sometimes at the beginning, the first couple of iterations, you will see certain oscillation of the error. Sometimes it overshoots, sometimes it decreases a little bit, but eventually it has to die out. This is very important because this is what you will use as a criteria to tell if your system is converging or diverging. So if we look here, this is the values that we have for this is for x1, x2, and x3. So you see here the value is going 0.99919, and the error is going to a very small value. This is 3.0001 and 4.0. So it's very close to the actual answer, which is 1, 3, and 4. This is after 6 iterations. Now I try to do the Jacobi method, and I did up to the 5th iterations, and I found the results as such. Just to give you an idea about x1, x2, and x3. So I found that after the 5th iteration, x1 is equal to 0.9639. So compare this to this. And x2, I found it equal to 3.0281. Compare this to this. And x3 is equal to 3.9971. Compare this to this. So you can see clearly that the Gauss-Seidel are faster. The conversion rate is faster. Both of them will converge. Eventually, both of them will converge. But the Gauss-Seidel, because you use the most updated value, they will converge. Someone will say, okay, but you started with 101, which is somehow close to the answer. It's 134, so it's the same order of magnitude. What if you start with something completely completely away from the final answer? What will be the solution? Let me see just if there's any questions I need to answer. Let me see here. It says here in our simulation assignment, if you tell us to stop once we reach a certain error, should we assume that you want us to stop once all values? Yes, when all the values within the error, not just one value. You have to check everything, and you will find that certain variables converge faster than others. Let's see, other question. How do you know that if they will converge at the global minimum instead of a local? Oh, okay, okay. This is an interesting question. How do you know if they will converge at the? Remember, these are linear equations, so they have only one solution. There is no multiple solutions. When we talk about optimization and multiple solution, this is a different story. We'll talk about this at the end of the course. But here we are solving only linear equations. Now, when we talk about nonlinear equations, we'll talk about that word as well later on. That how do we know that we converge to the right answer? Okay, these issues are for nonlinear equations and optimization. We will not cover it now. If the error begins to diverge, how can we solve using Gauss-Seidel? I will talk about this because we have to know first, understand what is the cause for the diverging. We will come to this. Could you remind me why we want to use the Gauss-Seidel method over the Gaussian elimination method? Okay, this is a good question. Okay, so why we need to use this? The Gaussian elimination has certain problems, as we have made like a round of error, which is here we can easily avoid. Then if you use the partial pivoting, then you will be able to be safe in the Gauss elimination. But sometimes you can even here in the linear system you can use the matrix inverse. You don't even need the Gauss elimination. But if you use the matrix inverse, sometimes your matrix can't be inverted, so you can't find the inverse when it has a lot of zeros. So then you have to use the Gauss elimination. Okay. Now this is, you may say that Gauss elimination may be if you use partial pivoting and avoid the problem of round of error, maybe it's much better than or better than the iterative methods. However, the iterative method is introduced here and can be used to solve linear equations that we know how to find the exact answer, but later on we will use it to solve non-linear equations, which is cannot be solved using any technique. There is no any closed form solution for them. So you may look to it as a way of education. You start with using it in a system that I can find the exact solution to check my algorithm, but later on I will use it in an algorithm that I don't know the final answer, which there it make more sense. Okay, is there is there initial value that we should use? Now we will answer this question in the coming example. How would the Gauss-Seidel method behave if the system has no infinite? It's the same thing. If the system has no solution, remember, there is no solution. Gauss-Seidel cannot solve this problem. But you will have no solution or an infinite number of solutions if you state the problem wrongly, if you write the equations in a wrong way, if you include, let's say, two loops in one loop, then you have an infinite number of solutions, or if you use the same equation but in a different format, then you have an infinite number of solutions. So this has nothing to do with the method, it is how you state the problem itself. Okay. Okay, so this is addressed most of your questions. So let me move on now and address about the initial guess. So let's see. I want to solve the same problem that we have, but instead of starting with something close, I will have something order of magnitude higher. Okay, so I will instead of the answer is in 1, 3, and 4. Here I'm starting 2 order of magnitude higher, 150 and 200. Does the system converge or not? We are very, very far away from the right answer. Okay, so we'll do exactly the same thing. We will start by restating the equations. One equation in terms of x1, x2, and x3, and then substitute. So this is the first iteration here. 1 minus this is x2 and this is x3. I will start with the initial guess. Then this is equal to 28. This is x1 and this is x3. So I will use the most updated value. And then this is the x3. So we'll got this. So they are a bit far away. But as I said, do not use the first iteration as an indicative of are you approaching or not approaching, are you converging or diverging. You have to keep doing few iterations before you come to this conclusion. So if you do that, this is the second iteration, third, fourth, and you can see clearly here we are converging. Yes, we are taking more steps, but all the answers, remember, this is 1, this is 3, and this is 4. So we are converging. Okay, we needed more 2, 3 iterations, but we converged. So it doesn't really matter. Okay, where we start. Okay, so is the world is always like nice and problem free like this, or we have to pay attention to? So what I did here, I want to solve the same equations. The only thing I changed, I interchange only these 2 equations, which is in real engineering systems, you might interchange the equations. One, you write it here and or there, so you might interchange the problems. Okay, so if this is the case, if we interchange the problems, what will happen? Okay, will we x2 and x3? So I did not do anything, just I moved equation 3 to 2, 2 to 3. That's all. And I will use the same initial guess I used in the second example 9, where it is proven that it will converge. Okay, so if I do the same thing here and we start with the first iteration, okay, things looks not clear. As I said, to never ever come a conclusion from the first iteration. But then let's see. As we move on, let's look to x1, x2, and x3. So it's very clear that we are diverging. Remember, the answers was 1, 3, and 4. But here we are like 5 million, here 1.947. So it is a very, very large number. So we are diverging. What went wrong? What we did, we just interchanged 2 equations. We did not change the variables. We didn't change anything in the equations. Just I did this, and I end up having this huge problem in my algorithm. So that will take us to what is the problem with Gauss-Seidel. The Gauss-Seidel is that it will not converge at certain condition. You have to meet a condition. You have to make sure that your equations satisfy this condition before you move on and you apply the algorithm. If they don't, they will not converge. And this is the system has to be diagonally dominant coefficient matrix. It has. Okay, so your system of equations, they have to form what we call a diagonally dominant coefficient matrix. What do we mean by diagonally dominant? It means that all the diagonal elements, they have to be more or equal to the summation of all other elements. This is very, very important. You have to have this. The elements, they have to be, all of them, each single element has to be more or equal. But for at least one of them has to be more, not just equal. Okay, so if you look to our matrix, this matrix, the original one. So this is the matrix A. So these are the diagonal elements. Okay, so you have to compare in absolute value. Is 12 more than A1, 2 absolute value plus absolute value if you want 3? Yes, this is 8, this is 12. So it is more or equal. It is actually more. If you look here, 5, this is 4. It is even more. And 13, this is 10. Okay, so the diagonal elements are dominant. They call dominant, diagonally dominant matrix. So for this, it guarantees the conversion. Okay. Now they could be equal for all the lines, but at least for one line they have to be more, not just more or equal. Now what we did here, when we write the system as such, what happened? The matrix will become equal to 12, 3 minus 5, 3, 7, 13, 1, 5, and 3. Okay, so these are now the new diagonal elements. If you go to the first line, 12, it is more than 3 plus absolute value of minus 5. So this is, I'm satisfying this condition. 7, on the other hand, it's not, and 3 is not. So in 2 lines or in 2 rows, I'm not satisfying. This is why the system did not converge. So this is something very, very important, that you need to make sure that your system is really dominant before you do anything. Now, let's ask ourselves a question. And I have been asked this question by some of you, that, okay, for the simulation assignment, do we need to check this? Make sure that our system is diagonal dominant. Okay. Now, let me do this exercise with you. I will do nodal analysis, I will do mesh analysis, and I will do KCL and KVL. And this will show us some of the advantage of using nodal or mesh as compared to KCL, KVL that we never talked about it in a circuit course. Remember, when we our objective, yes, we use small circuits to hand calculation for small circuit. But what if my circuit is 1,000 by 1,000? I mean, it has 1,000 nodes or 1,000 loops. Of course, I cannot solve this. And these are something that is available in reality. So we have to use a package like SPICE, for example. Do you know that PSPICE is based on nodal analysis? Why not KCL and KVL? What's wrong with KCL and KVL? We will learn another problem here, that the system, now why a nodal and a mesh analysis has certain advantage over KCL and KVL. Before that, let me see if there's any new questions. If we see that the matrix is not diagonally dominant, can we just rearrange the matrix to make it? Yes, of course. You need to do that. You should be able to arrange the matrix so that it will be diagonally dominant. Okay, let's start with here. Let's write the equations here for nodal. So let me apply nodal analysis. As we know, we have a reference. Okay, so this node, I know the voltage is Vs, so I don't need to apply KCL here. So I apply at V1 and V2. So this system will be 2 by 2. So let's apply KCL at V1. So assuming currents are leaving the node. Okay, I mean, this is just a good refreshing for you, but I will try to link the nodal analysis with the numerical, which is something I think very important, so that the course will not be dry. Minus Vs divided by R1 plus V1 over R2 plus V1 minus V2 divided by R3 equal to 0. Okay, so I will have like V1 as a common factor here, so we'll have 1 over R1 plus 1 over R2 plus 1 over R3 minus V2 1 over R3 equal to Vs 1 over R1. So this is the first equation. The second equation, KCL at V2. Currents are now, everything is leaving here. So it is V2 minus Vs divided by R5 plus V2 minus V1 divided by R3 plus V2 over R4 equal to 0. I will do exactly the same thing. So it's here minus V1 1 over R3 plus V2 1 over R1 plus 1 over R5 plus 1 over R4 equal to Vs 1 over R5. Okay, so I want to put this now in a matrix form. So this is matrix A. We will have here V1 and V2. okay, and is equal to, now Vs is a constant, so this becomes equal to Vs over R1, and this is Vs over R5. Okay, so let's see here. So what do we have here? 1 over R1 plus 1 over R2 plus 1 over R5, and here it is minus 1 over R3. I will address the question. Just give me a few seconds. Let me finish this, and then I will come back to you. This is minus 1 over R3, and here it is 1 over R1 plus 1 over plus 1 over R4, 1 over R3. Okay. Okay. Now what we noticed here, these are the diagonal elements. Okay, because the diagonal elements here, this is where we apply the node. It is summation of everything connected to that specific node. So always you will have this higher than the other elements. So if you use nodal analysis, it is guaranteed that you will have a dominant diagonal dominant matrix. So if I use nodal, I don't need to check this. Let me see. There's a question here. Okay, so it's a little bit a big one. Okay, sorry, you may have answered this, but I missed it. For the Gauss-Seidel method, for the simulation assignment, will we always receive a diagonal dominant matrix as input, or should we implement a part of the algorithm to swap? Okay, so what the question that you have in the simulation assignment is for mesh analysis. So this is like a system of a solver that you are developing using Gauss elimination, using Gauss-Seidel to solve any system of equations coming from mesh analysis. So the equation that I will be using, it has to be a mesh. So it's not generic for any application. It's only for this application. So in this case, yes, and we'll see in the coming example, you will find. So let's look here. Before we move on, let's move on here. And let me move to the next one here. Let's do the mesh analysis. Okay. Okay, let me do the mesh analysis here. So we'll have here 3 loops, okay, and those 3 loops, I want to apply KVL to them, okay, and I have the full answer, but I don't need to do the full answer. Let me write the matrix for you, the final matrix, the A matrix that you will find. It will be R1 plus R2 minus R2 and 0 minus R2, R1 plus R3 plus R1, or I think this is R2, this is R2, this is R1, and this is minus, you have the answer, the full answer in the notes, so I don't need to go through it again, minus R1 minus R3 and R1 plus R3 plus R5. Again, if you see here, these are the diagonal elements. Also, if you use mesh analysis, it will always guarantee that you have a diagonally dominant matrix. Regardless, if you name this I1, I3, I2, it doesn't really matter how you name them. Okay? Always you will have, always, it is guaranteed that always you will have a dominant matrix. So this is why in the simulation assignment, you don't need to do this check. If the question was generic, then yes, you need to check that. If not, then you don't have to check this. There are a few questions asking me as well here. If this example, if we write the KCL at V2 first, yes, if we start with V2 first, it doesn't matter. You will still have a diagonally dominant matrix. It doesn't really matter. You can try it, you can check, but it will be the same thing. Does mesh analysis? Yes, I answered this now. For the nodal analysis question, you are solving. What about KCL at VS? Oh, we don't. Okay, this is a circuit question. We don't apply KCL at a node that we know the voltage. Okay, so VS is a voltage that is given to us. We know it, so we don't. The only two unknowns we have was V1 and V2. So we don't apply KCL if we know the voltage. Now let's move to the last one, which is the KCL and KVL. Now, the KCL, the KVL, the problem of it is not a systematic method. In nodal, in mesh, it is systematic. You have loops, you name them, take KVL, and that's it. But in KCL, KVL, you can do KVL first, KCL mix. It's not really consistent. Okay, and if you one of the here I have made one solution of it, and this is the matrix I got here, which is R1, R2, 0, 0, 0, 0 minus R2, R3, R4, 0 minus R1, 0 minus R3, 0 R5, 1 minus 1 minus 1, 0, 0, and 0, 0, 1 minus 1, 1. Okay, so these are the diagonal elements. It's very obvious because I don't know if R1 is greater than R2 or not. I don't know if R2 is greater than R3 and R4. So depends on the values, I might get diagonally dominant mass and I may not. So this is one of the problems with KCL and KVL that you have if you use this to check this. This is one of the reasons, of course not the only reason, but numerically we prefer to use either nodal or mesh when we solve the system of equations.